And some of you might have remembered doing this in geometry, but that was a while ago. We'll do it in a little bit more depth here and consider some situations that you probably didn't do in geometry. But you might find this content familiar. So we're going to start by talking about the law of sines. So if you remember back in chapter 2 when we talked about right triangle trigonometry, we used things like SOHCAHTOA and the Pythagorean theorem to solve a triangle, right? Now, the catch there is that we had to have a right, yes, Gracie? Yes, of course. Is we had to have a right triangle in order to use those tools. So what the law of sines and law of cosines is going to allow us to do is to solve triangles that are not right triangles. Now, they still work on right triangles. It'd be kind of a crummy rule if it didn't still work on the things that we could do before. But now we'll be able to use them in other situations. So we're going to start with a derivation for this law of sines. So a derivation is just basically like explaining to you how we figured out this formula. So I'm going to start by drawing a triangle that's a non-right triangle that I'll label as triangle A, B, and C. So typically when we name triangles, we name them by their vertices, right? You remember that from geometry. Now, the convention when naming the side lengths for a triangle, one of the convention is we're going to name them with a lowercase letter, and we're going to use the same letter as the vertex that's opposite that side. So, for example, this side is opposite A, so we would call this side side A. And this side is opposite B, so we would call this side side B. And you can probably guess just by process of elimination then that this side is going to be side C. But it's really important that you're able to use this naming convention for the side lengths for your triangles, because this is the way that the law of sines and law of cosines formulas are formatted. So they're using this naming convention, so it's important that you remember to do that. It's not difficult, but it's different than using like segment names like you did in geometry, where you would have called like side A, B, C, right? Okay, so this is not a right triangle. So the first thing I'd want to do is to turn this into two right triangles by drawing an altitude here from one of the vertices. It doesn't really matter which one. Based on the orientation of my triangle, the easiest one to draw from an artistic standpoint is this one at vertex C. And I'm going to refer to this segment as H. So I formed two right triangles. I have triangle, for the triangle on the left, I can now use SOHCAHTOA to describe sine of angle A, since it's a right triangle. So sine of A is going to be opposite over hypotenuse. And on the right triangle on the right, I can do the same thing with angle B. So sine of angle B is going to be opposite over hypotenuse. Everybody's okay so far? Notice both of these contain one side length that's in common. That would be the side length H. So I can treat these two equations as a system of two equations and use substitution to combine them into a single. So I'll do that by taking the first equation and multiplying both sides by B. And the second equation, I'll multiply both sides by A. Now that they're both equal to H, I can set them equal to each other. And then the usual convention is we would divide both sides by AB. So we'd be left with sine of angle A over side A equals sine of angle B over side B. And if I repeated that process and drew my altitude from either angle A or angle C, I would be able to get a second equation that says sine C over C is going to be equal to one or the other. So by the transitive property, they can just put them all equal to each other. And this is what we refer to as the law of sines. So that's our law of sines. We can use this for non-right triangles, which is excellent and quite handy. So let's look at a couple of quick examples here, and then we'll move forward. Sound okay? All right. So a derivation like this, again, would I ever ask you to repeat something like this on a test or a quiz? No. The derivations are just for you guys so you can better understand kind of like how we come up with these formulas and why these formulas are true. It's not something a skill that I would ever ask you to repeat. Okay. So a typical question for this chapter might look something like this, where I ask you to solve the triangle ABC, where angle A is 32 degrees, angle B is 73 degrees, and side C is 13 inches. When I start a problem like this, typically I like to start by drawing a picture and labeling my parts. So I know that angle A is 32 degrees. I know that angle B is 73 degrees, and I know that side C is 13 inches. And remember, when we say solve a triangle, we're just looking to find all the side lengths and all the angle measures, right? So I need to find angle C, side A, and side B. One of those three things to find is trivially easy. Which one is the super easy one to find? Angle C. How do I find that? Yeah, so I can just use the Triangle Sum Theorem that says the interior angles of a triangle add to 180 degrees. So if I know two of the angle measures, I can find the third one really easy. So when I do that, I get 75 degrees. Everybody's okay there? Okay, since this is not a right triangle, though, to find the side lengths, I'm going to have to use the law of sines. In order to use the law of sines, I need to have an angle measure, or I need to know an angle measure and the side length that's opposite that angle. So the situation in this case, I know angle C and I know side C, so I have to use that as part of my law of sines. And let's solve for side A next. It doesn't really matter. So there's my law of sines. Notice that I just forgot about the side, or the stuff involving angle B and side B, because I don't need to do that right now. I can just pick the fractions from the proportion that I want to use. And when I have one fraction equal to another fraction like this, we call this a proportion. The easiest or gold standard way of solving a proportion is to cross multiply and divide. So that's what we'll do here. You probably remember doing that in your geometry class when you dealt with similar triangles. That 13 was looking a lot like a B. So we cross multiply, and then we divide by sine 75. And when I type this into my calculator, what mode would I want to make sure that my calculator is in? Degree mode. How do I know that I need to be using degree mode versus radian mode? Yeah, in the problem, the angle measures we're given were in degrees. So they told us in the question. So there's my side length for A. Now to find my side length for B, can I use the Pythagorean theorem? I know two of the side lengths. I can't use it. Why not? It's not a right triangle. And you're probably thinking at this point, like you've said it, this is not a right triangle about 8 times now. I'm not stupid. I haven't forgotten that. And it's like, well, every year somebody starts overlooking that at some point and makes a big mess out of something. So I'm going to just keep reiterating the fact that we can, the tools that we can use for right triangles and the tools we can use for non-right triangles are different. So so to find side B, we'll set this up kind of the same way. And I'm going to skip showing all the work we did to get there and just go straight to this spot because it's almost identical work as the previous problem. So the setup and then what you're actually typing into the calculator I think is enough at this point since you've done one all the way. We did one part of this all the way through. Everybody feel okay here? Good. So this situation that we just covered, if we look at this, we knew an angle, another angle, and then the side in between those two angles. If we think back to geometry, this was a congruent triangle situation called angle side angle. You remember that we had a bunch of these congruent triangle theorems from geometry. This was one of those 3. So any situation that we have that corresponds to a triangle congruence theorem is something where it's going to be easy to solve the triangle. Okay? So the other triangle congruent situations were like side angle side, side side side, angle angle side. Those ones will all be relatively easy to handle. Not all of them we can use the law of sines on, but we have law of cosines that we'll talk about later. Do you remember the situation that was not a triangle congruence theorem? That was this SSA situation where you have a side, and then the angle that's not in between the two sides. That was not a triangle congruence theorem in your geometry class. This situation, though, should be something I can use the law of sines on, but we're going to have to be very careful in this situation, which brings us into the next section. And this situation, this SSA situation, is called the ambiguous case. And just to illustrate why this SSA does not have a triangle congruence theorem attached to it, let me just kind of illustrate that to you. So let's say that we have some isosceles triangle here. Everybody's okay with that? Just an isosceles triangle? And I'm just going to draw a segment here that's not an altitude, like this. And call that point D. notice that triangle ACD is not congruent to triangle BCD, right? We can see that clearly. Nobody's got a doubt about that those two are not congruent. However, we have that AC is congruent to CB. We have that angle A is congruent to angle B. And we have that CD is a part of both triangles. That would be our SSA situation, right? So just having SSA does not guarantee that you have two congruent triangles, because we can see clearly this is a situation where the triangles aren't not congruent, but they meet that SSA criteria. Everybody's okay with that? So the tricky part here is, for us, if we have an SSA situation, it's possible that we can have two answers. So like, which triangle am I really solving for if all I know is the measures for side AC, for side CD, and a measure for angle A? I don't know which triangle I'm supposed to be finding. In fact, both of those triangles are plausible. So let's talk about the different situations. So if the given angle, the angle that you're given information about in the problem, is obtuse, actually let's combine this. Let's just say the given angle is greater than or equal to 90 degrees. So let's include a right angle with that also, because the same thing is going to be true. So there's two situations that we can run into if the angle or the given angle is not acute. So the first one is if the given side that's opposite that given angle is smaller than the other given side. That's impossible to have a triangle formed. Why would that be the case? Well, if the given angle is not acute, that means that none of the other angles could be 90 degrees or bigger, right? Those other two unknown angles can't be bigger than 90. Everybody agree with that? So what that means is the side opposite that non-acute angle has to be the hypotenuse, right? Because the angles or the side lengths are proportional to the angle measures. So like the longest side is opposite the biggest angle, the shortest side is opposite the shortest angle, and the middle side is opposite the middle angle. Everybody remember that from geometry? Or you'll take my word for it now that I've reminded you. So here we'd be saying, okay, we have the biggest angle, but opposite that isn't the biggest side. It's, in fact, what should be the hypotenuse is not the longest side. That's impossible. Can't make a triangle out of that. If that's not the case, so if the side opposite that given angle is the largest, then you just get one triangle and you can proceed normally. Nothing tricky happens. So the second situation is if that given angle is acute. Okay. So if we have an acute angle and the given side opposite that given angle is greater than or equal to the other given side, then just one triangle is possible. So again, nothing strange is happening. Everything proceeds as normal. Oops. So if that given side is shorter than the other given side, we don't immediately know what's going to happen. You could have no triangles possible, you could have one triangle possible, or you could have two triangles possible. This situation is the one that we specifically refer to the ambiguous case as the ambiguous case, because just from the given information you don't know how many solution sets you're really going to be looking for. So let's talk about how we would determine that. Okay? So let's do that with a specific example. Okay. So let's say that we want to solve the triangle PQR, where angle P is 56 degrees, side P is 16 degrees, and side Q is 19 degrees. So just filling in what we know. We can see that this is an SSA situation, right? Because the angle is not in between the two sides that are given. That's how you can tell the difference between an SSA and an SAS. So since this is a side angle or a side angle situation, I have to check to see which case it is. So angle P is less than 90 degrees, and then side P is less than side Q. This is that ambiguous case situation that we've been talking about, right? We have an acute angle that's given, and the side opposite that acute angle is shorter than the other side that's given. So to determine the number of triangles, this is what we do. We set up a law of sines. So we have sine of P over side P equals sine of Q over side Q. And if we cross multiply and divide to get sine Q by itself, that's what we're going to use to make that determination. So when I fill in these values, and I type this into my calculator, I get 0.984. If this number is greater than 1, 0 triangles are possible. If it's equal to exactly 1, 1 triangle is possible. And if it's less than 1, 2 triangles are possible. Okay? So to determine the number of triangles, again, what we're going to do, we set up a law of sines. And we get that unknown value for sine by itself, and we look at the value that that sine of the angle, unknown angle, gives us. If that value is less than 1, 2 triangles. If it's equal to 1, that's 1 triangle. If it's greater than 1, that's 0 triangles. Should be easy to remember that, because if I have the sine of an angle, well, I remember that the range for sine is between -1 and +1, right? So if the value for sine is greater than 1, that's impossible. That's saying that there's no triangle possible because you're getting a value for sine that it can't have. If it's equal to exactly 1, well, I remember between 0 and 180, sine is equal to 1 just one time at 90 degrees. If I look at between 0 and 180, though, a sine value between 0 and 1 happens twice, right? Because sine is a hump. There'd be 2 values that sine could have. You know what I mean? So if you go back and you think about the graph, it's easy to remember the rule there. Or you could just memorize it. Like, it's not that difficult of a thing to memorize. Okay. So let's finish or continue solving this now, since we've determined that we are in this situation. Oh my goodness. So the way I like to do this is I'm going to just make 2 separate columns, one for each triangle, and kind of do the work for each of these situations in its own separate column. And we're going to solve for angle Q, angle R, and side R. And I'm going to put subscripts on these so that it's easy for me to keep track of which value goes to which triangle. Is everybody okay with that idea? So that's just some notation that helps me kind of keep things organized. So to solve for angle Q1, I'm going to take that information that I had before, And to solve for the angle Q1, then I'm going to take the sine inverse of both sides. And when I type that into my calculator, I get, oops, approximately 79.893. Finding Q2 then is very easy because it's just the supplement to Q1. So in that case, that's 100.107. Now that I have Q1, R1 is going to be easy to find. And similarly, R2 will be easy to find. So far, so good, everybody? And then to find the side R1, well, I'll just use the law of sines again. So I'll do sine of P over P equals sine of R1 over side R1. And when I cross multiply and divide, I get that this is about 13.432. And similarly over here, I'm going to set up a second law of sines, but I'm going to be using R2 in this situation. Which comes out to be about 7.817. Any questions on what we've done here so far? Okay. This is where we're going to stop here for today. We'll finish Chapter 7 next class. I know that feels fast, but Chapter 7 is a pretty short, wimpy little chapter. We really just have 3 formulas that we have to get using. And really what we did today was the hardest part of the entire chapter, with the ambiguous case part is by far the hardest thing in this chapter. Okay? So homeworks. From the problems, you guys should be able to do 1 through 14 after today. So I want to point out to you on 5 through 10 that you don't have to do a whole lot there. It's not asking you to solve the triangle, just to determine whether it's 0, 1, or 2 triangles. So you don't actually have to solve those triangles and find out the values. You just have to determine how many triangles are possible. So again, for these homeworks, you can do this in OneNote, that's fine. Or you can do this on a separate sheet of paper and then take some pictures and drop those into OneNote. If you need help doing that, let me know, or ask one of your other classmates that tells you that they know how to do that, because a lot of people did that last semester. It's not too difficult. Probably the easiest thing to do is use your cell phone, take pictures of your pages, email those pictures to yourself, and then drop them into OneNote. So it's not too difficult to do that if you are a tactile pen and pencil person. So we have, 15 or 20 minutes still left in class. I'm going to leave these problems here posted, so if you'd like to start on things, you can start on things. That would be my suggestion, because why wait on it, right? It's one less thing. Saves you 15 or 20 minutes over the weekend. Again, you can look at these on your tablet also. They're in the content library, all the problems. And I will put this on PowerSchool, or check to make sure that it's on PowerSchool. I think it's already on there. On the calendar as an assignment due for Sunday. Yes, okay, so it's already there.